Okay, so there are a few people in the chat already. I think we're gonna get started. I'm gonna start by the introduction, and if some more people enter afterwards, it's fine. So hi everyone, and welcome to our last seminar of this school year before the summer break. Today we have Jorge Sánchez-Segovia from the Autónoma University of Madrid. He did in the Autónoma his bachelor's degree in physics and his master's in theoretical physics, and now he's doing his PhD with Álvaro Alhambra. The floor is yours, Jorge.
Thanks for the introduction, Bea. Today I want to talk about a work Jan, Álvaro, and I did, which is already in the archive if someone is interested. So what am I talking about today? Well, I want to talk about long-range interacting spin systems. More concretely, those in which the interaction strength decays with a power law on distance, where alpha parameterizes the power law, which is an important parameter that we will talk more in detail later. The thing is, why would we be interested in the first place to study these systems? Well, these kind of interactions are present in basically a great percentage of nowadays promising quantum information processing forward. For example, Rydberg atoms, that as we know, they are really good in terms of gate speed and simulating gauge theories, or for example, trapped ions, which have high fidelities, and they are very mature in terms commercially speaking, because for example, Quantinuum or IonQ are companies which are nowadays developing this kind of softwares, or also cold atoms and molecules, which are very good in terms of scalability. So from the point of view of quantum information and quantum computation, we are pretty interested in this kind of systems. But leaving aside this kind of motivation, we can also be motivated to study them just from a fundamental perspective, as these kind of systems present really exotic quantum phenomena, such as spin squeezing, which consists in the reduction of the uncertainty of one of the components of the spin of quantum uncertainty, or really weird properties such as ensemble inequivalence and negative heat capacities. So we are also, from a fundamental point of view, we are interested in them. Therefore, at this point, I want to think that we are all motivated to study this kind of systems, and rather than focusing on a concrete and a specific system which has long-range interactions, we are motivated to study general properties of long-range systems. So we are going to start from first principles, and the only thing we are going to assume is that the Hamiltonians that we study have this form, which is a sum of individual terms up to k-body interactions, such that the norm of the individual terms of the Hamiltonian are upper bounded by the distance, with a power law on the distance, where G is a strength constant, an energy constant, and alpha again parameterizes the decay. Notice that alpha is a really important parameter, because if we make alpha to be 0, we will actually have an all-to-all interaction independence on the distance. So in the alpha parameter, basically, if we can, from alpha equals to 0 to alpha equals the dimension, it is the so-called in the literature strong long-range regime, in which the locality of the system is really reduced, and we have these all-to-all couplings more or less, and it's in this regime where the most exotic phenomena appears. But we have a mean field description to tackle this kind of systems. Notice also that if we make alpha to be infinity, the interaction will be only non-zero for nearest neighbors, and that is what we call a local system, which is basically that we only have a finite and the spin will only interact within a local region. And well, the thing is that a classical example of a local model is the well-known Ising model. And well, under the assumption of locality, there has been a lot of development in terms of algorithms, mathematical physics and condensed matters, and we have a plenty of results which hold for general local models. For example, we have Lieb-Robinson bounds, which upper bound the velocity of propagation of information in local models, in lattices. Also, we have exponential, we have the decay of correlations, and well, a lot more, basically. Because starting from these assumptions, makes combinatorics and makes treating analytically these systems really easier. But normally, when we study spin lattice systems, we are trying to model basically atom or ion lattices. And the thing is that we have to take into account that in real lattices and in real atomic systems, we have electromagnetic forces, dipole-dipole interaction, Coulomb, and all of these interactions decay with a power law on distance. So basically, it is really physically motivated to study long-range interactions, and more concretely, the weak long-range regime, in which alpha is not so small. So we expect some locality properties to hold, but we want to study rigorously what happens with long-range interactions. And there, because of the difficulty of analytical treatment of long-range interactions, there were a lot of results that are valid for local models, but not for long range. But in the recent decade, some results have been extended, such as Lieb-Robinson bounds or decay of correlations. But there are a lot more which have not. More concretely, what is known in local systems and not in long range, or what has been performed in local and not in long range? Well, for example, there are plenty of really important results, such as the fact that high temperature Gibbs states are entangled and efficiently preparable, learning results also in learning quantum Hamiltonians from Gibbs states, also results in polynomial sampling of high temperature Gibbs states. Well, a lot of really important results that we have on local models, but not in long range, and they all have a common characteristic, that is that they follow from the analyticity of partition-like function of this kind. For example, look at this function and notice that if we put the quantum state to be the identity and we put beta to be real instead of complex, we recover the canonical typical partition function. But we will keep it general as we are interested also in maybe some dynamical quantities that we will talk about later. So let's keep it general like this. And we are interested in showing, therefore, the analyticity of these kind of functions. A way to show this is to show that the Taylor series converges, and consequently, the function will be analytical. But if we expand in Taylor, we notice that the real extensive graph of long-range models makes that, and also in short range, makes it a really non-trivial task to count all these and to control all these contributions. So how can we show that this expansion converges in the first place? Well, now I'm going to introduce our technical tool, which are cluster expansions, but let's start step by step. Let's look at the Taylor expansion of the partition function right here, and notice the following. We have that each individual Hamiltonian corresponds to an hyperedge. For example, here theta 1 is these three sites, theta 2 this 4, theta 3 this one, theta 4 this one. Okay. Notice that the following. if the quantum state that we are studying is a product state, for example, it could be the identity if we are studying the partition function, the trace for this individual term factorizes. Why? Because theta 2 and theta 4 have no common support. But on the other hand, theta 1 and theta 2 are connected, and the trace therefore does not factorize. So at this point, it is useful to define polymers, which will be basically sets of connected hyperedges. We have, for example, theta 1, theta 2 to be a polymer, but also theta 2 and theta 4 to be, they are also polymers because, okay, they are small sets, but they are also. And the thing is that we notice that each term of the expansion can be corresponded to a set of disconnected polymers. So we rewrite the Taylor expansion with some technical work that it is not worthy to go through the details, but basically we have then that our partition function is a sum overall set of disconnected polymers, where we have a productory of a certain weight for each polymer, and the fact that we have a productory on polymers is related to the factorization of the trace. I've explained before, and this weight will be proportional in beta as in the following way: beta power to the number of hyperedges of the polymer, and then the trace of the corresponding polymer. So, okay, we now have this thing right here, which basically we have to, if we want to control this kind of sums, we have to sum over sets of disconnected polymers. But it is also not worth to go through the details. But basically, if you take the logarithm of the partition function and do some magic, basically, so mathematical physics magic, you can notice that if you want to account for the cluster expansion of the expansion of the logarithm of the partition function, you have to sum over set of connected polymers, and these sets of connected polymers will be clusters. And this function here is basically the Arsel function, which vanish if the set is disconnected. And this is the so-called cluster expansion, which is our main technical tool for this work. And the thing is that we prove the analyticity of the logarithm. Well, we are also proving the analyticity of the partition function itself. So, okay, we want to prove now the analyticity of the logarithm, as we want to sum over sets of connected polymers instead of set of disconnected, because there are more of them. But the thing is, okay, how can we prove the convergence of this object here? Still not a trivial task, but thanks to Koteckỳ and Preiss, which in 1986 developed this criteria. They show that under certain conditions, the logarithm is analytic and has a convergent cluster expansion. More concretely, if exists a function which goes from a combination of a configuration of polymers to a real number, such that you have for any given polymer gamma star of the configuration, the sum over polymers connected to this gamma star of this quantity right here, an absolute value of the weight multiplied by the exponential of the function, is smaller than the function evaluated on gamma star, and this is satisfied for each gamma star. Basically, you obtain this upper bound, which is closely related to an upper bound of the logarithm, and you end up concluding that the logarithm of the partition function is analytic and has a convergent cluster expansion. So, given that criteria, basically our main technical result and our main technical contribution is to show that if we have a Hamiltonian, which is a long-range Hamiltonian, such that we are in the weak long-range regime, such aka alpha greater than the dimension, the logarithm is analytic and has a convergent cluster expansion for inverse temperature smaller than this threshold value. And basically, it means that if you have your fixed order M cluster expansion, aka the expansion up to order M, and you can upper bound the absolute value of the difference of that fixed order expansion with the logarithm to be exponentially decreasing with the order of the expansion if beta is small enough. So, okay, this is our main result, and now I want to notice the following. why our result is only valid for alpha greater than the dimension? Well, the thing is that this quantity here, u, which appears in the threshold value, is basically the sum. You fix a site on the lattice and you sum over all the contribution which have a fixed distance with respect to that site, and those contribution grows as the surface. So basically, the sum is proportional to a sum over all natural numbers of n power to the dimension -1 minus alpha, which only converges for alpha greater than d. So that explains why our result only works in the weak long range region, for the audience to have an intuition on why exactly. And now I want to sketch the proof briefly, or in order to understand which was the technical difficulties that we faced to do this job. And I'm going to sketch the proof only taking account two-body interactions, because if we take into account k-body interaction, the explanation is it's less clear, and you need some few extra steps. But for showing the proof in the two-body case, capture the essence of the proof. So I will do it in the two-body case. And notice that we wanted to show that this sum over here is smaller than this function. This is basically the Koteckỳ and Preiss criteria, but we want to show it for a function which is not non-trivial. Why? Because if we choose the function to be system size powered to the system size, basically to prove that is really, really easy. But with that, we won't be able to show that the sum converges, because this explodes. So we have to choose A to be big enough for the criteria to be satisfied, but small enough for the criteria not to be trivial. And in our case, we choose the function of the polymer to be the number of non-repeated edges, this thing here. And also we notice that this sum here of this quantity, overall polymers connected to gamma star, can be upper bounded by the sum over all edges of the polymer gamma star of the polymers connected to each edge. So basically, we show that to prove our Koteckỳ and Preiss criteria with our function is equivalent to prove that the sum over polymers connected to any edge of the lattice will be smaller than 1. So we want to prove this. And now the thing that we do is we order the sum in terms of the size of the polymers, and we also put the value of the weight, and we conclude that we have to sum over fixing the size of the polymer. We have to sum this productory of edges of the individual Hamiltonians, the overall polymers connected to a certain edge. Notice in the picture the edge is this edge in red, and this is an example of a polymer connected to this edge. And notice the following: if we, instead of summing overall polymers connected to that edge, we sum overall polymers connected to each side with a fixed number of edges, we basically upper bound this quantity here. So basically what we have to learn how to do is to be able to sum over polymers connected to a certain site, aka this sum here, which we'll call SI. So we have to sum overall polymers connected to a certain site, the productory of edges of this concrete polymer of the individual Hamiltonians, fixing the number of edges of the polymer. And the thing is that in the finite range case, this the region is naturally, as you can only have nearest neighbor interactions, basically the region in which to find polymers connected to a site is bounded in space, because you can only go m steps away from the site. So you have to count polymers in a finite region, and this is considerably more easy, or is considerably easier than in the long range case, in which you have all-to-all connectivity. So you don't have this bounding in space, and the counting of polymers is really more difficult. And so how to count this number of polymers, because we have a lot of contribution. Okay, this is basically the main reason for which we have a lot of formal result on finite range related to the partition functions, but in long range this was still an open problem in mathematical physics. And now I wanted to reach to this point for you all to see which is the main technical difficulty that we were able to solve in this work. So at this point, let's notice the following. We can switch the notations because we can talk of the Hamiltonians in terms of edges, but also in terms of pair of vertices. And we can upper bound the norm of the Hamiltonian using the power law condition of our initial assumption. So basically, we upper bound the productory that we have to sum over as a productory of tensors, which we will call J tensors. And the key of this work, the main thing that makes easier the rest of the calculation is noticing each of these productory of tensors have a tree structure rooted at A. Let me explain maybe better. Notice at left, we have an example of a polymer, which is a polymer connected to the site A. And we notice that we can map it to a rooted tree on arbitrary indexes. We have here concrete sites, but here we have arbitrary indexes. And we perform this map. We are able to do it. We can make this correspondence. Notice that if the polymer is different, you can also do this map, but you may have to map it to a different rooted tree structure. So the topology, somehow the topology of the polymer makes, depending on the topology of the polymer, you map it to a rooted tree structure or different or another. But for each polymer, you can make this map. So if you are, and notice the following, if you are given a specific kind of rooted tree on arbitrary indices, this, for example, this one right here, and you sum overall, you sum all these indexes over all the lattice, you basically recover the sum of all the polymers that can be mapped to this specific kind of rooted tree. So if you sum this, you sum overall kind of rooted trees, and then overall lattices, overall the sides of the lattice, to say in another way, you sum overall kind of rooted trees, overall sides. This quantity right here, you basically reach an upper bound of the sum Si. And how to sum this thing here? Well, we can use the fact that the number of rooted trees given a certain number of edges due to some combinatory relatively standard result can be upper bounded as 4 power to the n, and this sum over all sides of these tensors due to the long range decay can be upper bounded by gu dot u power to the n. So basically, given mi edges, you can upper bound this sum by this thing here. And this was the main technical part, the main technical contribution. And if you plug this sum in the upper bound that you wanted, in the sum that we wanted to upper bound by 1, we notice that we obtain a geometrical kind of sum, which is smaller than 1 if beta is small enough. So what we conclude is that for high enough temperatures, the Koteckỳ criteria, Koteckỳ-Preiss criteria is satisfied, and the cluster expansion therefore converges. So this was our main result, and I hope that it could be followed more or less the technique that we used. And we also did a slight generalization, which is basically instead of only having one exponential inside the trace, having a productory of exponentials. And basically, we were able to get an analog result, which is that also in the weak long range regime for a sum of absolute values of the parameters small enough, this threshold temperature, we also have the convergence of the cluster expansion, which in this case is a multivariate cluster expansions, which with one variable corresponding to each of these lambdas or variables. So, but we basically are able to prove something similar. So great news, the technical part, the most technical part is over. And now I'm going to show why we were motivated to do all this thing in the first place and talk about the results. And the first result I'm going to talk about is a classical algorithm for estimating partition function. The idea is not so incredible. It's just if you compute the cluster expansion, you get an estimation of a partition function. So basically, we are going to compute the cluster expansion of up to certain order. And the first step is, well, we firstly need to list all connected cluster of size m. And for that, we first need to enumerate all connected hypergraphs in the lattice of size at most m. Okay, for doing that, we will first fix a site and notice that for constructing an hyperedge connected to the site, we have n-1 power to the k possibilities at most. Then at most we have n-2 power to the k overall k sites. And if we continue doing this, we notice that the number of steps for counting all these clusters is upper bounded by n power to the, being the system size power to k, being k referred to the k body interaction, multiplied by m factorial. And this step is really different with respect to the local case, in which we have an exponential on m steps, which is a lot of less steps. So this is the step which differs a lot with respect to the local case for this semi algorithm. Because, for example, if for each hypergraph, we can enumerate all polymers of site at most m, and from that list of polymers, we can create all connected clusters, also in exponential on m time, both for long range and for local. And the next step, well, notice that the cluster expansion up to order m has this look like this right here. So we need to both compute the Ursel function and then compute the weights, and this both for long range and short range can be done on exponential on m time. And finally, you have to choose m, like the order, meaning the order of the expansion, such that the difference between your expansion and the logarithm is smaller than certain error epsilon, and you basically obtain a sub-exponential classical algorithm. But for long range models. So okay, let's compare this algorithm with other algorithms for estimated partition function of long range models, which are now in the market. Okay, last year, Kuwahara and his team were able to get an efficient algorithm that is classical, which is valid for alpha is greater than 2 and for any temperature, but it only works for one-dimensional systems, and it has also a sub-exponential complexity. Our work instead, well, it's also classical, but the regime of validity of alpha is better because, for example, in the one-dimensional case, our work also will serve for alpha greater than 1, but the main difference is that it only works for high temperatures in comparison with this algorithm, but for arbitrary dimensions. This one up here is only valid for one-dimensional system, but it has the same complexity. There is this other work which is really interesting to compare with, which is also from last year, which is a quantum algorithm that performed the same task, but in a worse alpha regime, in a worse temperature regime, with more strict constraints, also for arbitrary dimensions, but it can do it in polynomial in a number of steps, and therefore is significantly more efficient than ours. So at this point, can we conclude or can we think that there may be a quantum advantage for this concrete task? Okay, this is an open question that we leave. And now, leaving aside well, leaving aside algorithmic results, we're going to talk about more fundamental results, more concretely about the statistical properties. Well, notice that quantum physics is naturally described by probability theory. And this is especially useful. This is an especially useful approach for quantum many-body physics when you cannot follow the specific properties of each constituent, but you will rather try to follow the collective phenomena and the emergent properties. So, well, notice that given a quantum state, the distribution of possible measures of an observable A is defined like this, like the trace of the projection of this subspace of the quantum state. And this distribution have moments like this, like moments of order m, which is basically the trace of the operator power to the m of the observable multiplied by the quantum state. And there are this function, which are the moment generating function, which have this form. And notice that, well, and the special thing about this moment generating function is that by approximating them, we get a lot of really nice probability theory important results. And notice that these functions are really similar. Or well, they are basically in the same. They have the same form that the functions, the partition-like function that we are controlling via theorem 1 and theorem 2. So we can approximate these moment generation functions with our theorems and get some probability theory results. And the first one I'm going to talk about is the Chernoff-Hoeffding bound. So we can state that in the weak long range regime and for high enough temperatures, we basically have that the probability of a certain observable to be away from the thermal mean at a delta distance decrease exponentially with this distance. So basically, you have that for relatively high enough temperatures, the observables will be really, the outcomes of the observables will really be concentrated around the mean value, and this corollary follows from this bound on the logarithm of the moment generating function, which we were able to do with our results. And it does imply something really special, which is the equivalence of canonical and microcanonical ensembles. The thing is that we have examples of ensemble inequivalence but only in the strong long range regime. So this, as a matter of fact, this gives us the intuition and that our results won't hold in the strong long range regime, because if they hold, therefore we could show that we could show Chernoff-Hoeffding bound and consequently ensemble equivalence. So this gives us the intuition that our results do not work in the strong long range regime, not because we are not smart enough, not because our not because of we are not able to prove, but rather it seems to be a fundamental property of nature. And there's this other really important result, which is Berry-Essen theorem, which is basically a strong version of central limit theorem for those of you who that may ring a bell. And basically, we consider the cumulative distribution function, which is the integration of the probability of distribution of a certain observable, where our quantum state will be either product state or the Gibbs state at high enough temperatures. And if we compare this distribution with the corresponding Gaussian distribution using the Gaussian cumulative distribution, and we assume that the state will that the variance of the state will grow will be lower bounded by a system size scaling, which is not a really special assumption, because only if you have really special symmetries and really special states this won't hold, but this in the general case will actually hold. Basically, given all these conditions, the difference between the Gaussian cumulative distribution and the cumulative distribution of your distribution will be bounded by the variation error, which is this thing right here, which will scale with system size as n power to the -1/2. So in the thermodynamic limit, we expect our distribution to be perfectly Gaussian. And this theorem follows from a bound on the partition on the characteristic function of this kind. And a really especially interesting case is the Gaussianity of the density of states. The density of states is this quantity here, which very typical in very commonly introduced in solid state courses. And is basically the spectrum. Well, basically it describes the spectrum of energies, and the Gaussianity of the density of a state have different implications for thermalization properties, simulation of pure states. So, okay, we are motivated not only from the fundamental point of view to see that the density of a state is Gaussian. And what we will do is also study we'll try to estimate the density of states with numerical methods for the long range Ising chain, which is this model right here, which satisfy our assumptions. And it's one-dimensional. And at this point, I'm going to do a small interlude. A lot of you may be familiar with this kind of techniques, tensor networks techniques, but they are a really efficient approach for especially in one dimension for simulated quantum strongly correlated matter. And we have MPAs which approximate the states, and MPO which approximate operators. Well, look at the wave function here. Notice that the number of parameters to determine exactly the wave function coefficient, which can be seen as a vector, it grows exponentially with system size. And this is the so-called quantum many-body problem. And this is why you cannot exactly diagonalize for more than 20 sites, so 24 sites even if you have a really good computer. And the thing is, if you can rewrite the degrees of freedom of this coefficient, which can see as a vector, as a productory of a tensor for each side. And we will fix the bond dimension, the dimension of each tensor. We will not permit this tensor to have a really really big dimension. And if we fix the bond dimension, we basically need a polynomial size of parameters to describe efficiently or to describe our MPS. So we reduce the cost, the algorithmic cost, significantly. And for MPO for operators, you can follow a similar reasoning. And the thing is that by doing this approximation and fixing the bond dimension and using this kind of ansatz, you represent really efficiently the low entanglement spectrum, which is this corner here of the which satisfy the area law of the Hilbert space, which actually turned out to be the most relevant physically because it's normally where ground states are and where the relevant physically things happen. So it is well, this is why these kind of techniques are really standard today and really used. And the thing is that as the density of a state can be rewritten as a Fourier transform of the trace of the time evolution operator. So our numerical method to estimate the density of a state will be basically to get to use an MPO efficient representation of the time evolution operator and perform a numerical fast Fourier transform on it, and then estimate the density of a state. So we did it actually, and we plotted the density of states for as a function of energy for different alphas, as we can see here in the local case also, and for different system sizes. And we observe, and if we fit our data with a Gaussian fit, we observe that the fit captures really well the data. So we observe the Gaussianity of the density of states. So the numerical results are consistent with our analytical proofs. Also notice that the density of states when increasing the system size gets sharper and sharper, and this is because because if you normalize your Hamiltonian correctly to not scale with system size, the variance decreases when increasing system size. And we observe that the Gaussian fits capture the data really well, even for alpha equals 0.5, which is in the strong long range regime. So maybe this Gaussianity of the density of a state, it seems to be something also which also holds in the strong long range regime and not only in the weak long range regime, which is where our analytical proofs work. To look at that into more detail, we plotted the residuals of the Gaussian fit with the numerical estimations for different alpha and for varying also system size. And what we observe is that when we increase alpha, basically the curves go down and go down. So we conclude that Gaussianity increases with locality. And also we observe that the error seems to decrease unless we are in the strong long range regime, in which the error keeps small but more or less constant. So maybe our analytical results are unlikely to hold in that regime. Also, I want to talk about what our results imply in terms of the criticality of systems. And the thing is that, well, and firstly, I'm going to talk about thermal phase transitions. Well, the analyticity of the partition function implies the absence of thermal phase transition for high enough temperatures, higher than the threshold value. And we concluded that, and this conclusion, how does it compares with previous knowledge? Well, it was known but for a wider it was known. This was known because of the long range extensions of Merry-Wegner theorem, but in a smaller range of alpha. So we were able to improve our results. That results in that sense. However, those results are better in terms of temperature range. So yes, our results complement those long range extension of the Merry-Wegner theorem. And our results are also consistent with previous numerical results. And for those of you who are familiar, there is this special kind of thermal phase transitions, which are BQT transitions, are also included by our analysis because these transitions leave the partition function smooth, but not analytical. And these were observed into the long range systems, but in temperatures which are 1 or 2 order of magnitudes below our threshold. So our findings are consistent with those of the literature and also complementary to recent results discarding thermal phase transitions at any temperature, but in one dimension for alpha greater than 2. Okay, other kind of criticality that we were able to constrain are dynamical phase transitions. Because notice that if in the logarithm of a partition-like function we put beta to be purely imaginary and we put the state to be a product state, we recover a Loschmidt-Echo, and the QPTs basically are combined by singularities on this function right here, closely related with the Loschmidt-Echo, and they are basically real-time analogs of thermal phase transitions. And as we are able to show that for small enough temperatures, the Loschmidt-Echo is analytical. Therefore, we conclude that we won't have at short enough times in general long range models and also short range dynamical quantum phase transitions. Finally, I want to discuss the constraint that the work makes on another kind of critical phenomena, which are excited state quantum phase transition, which it's probable that not a lot of you are familiar with this kind, so I will explain it a little bit. They are because they are more weird, and they are basically singularities in the density of a state at certain energies, which indicate a qualitative change in the structure of the excited states spectrum. We have a lot of less theoretical and experimental knowledge of this kind of transitions in comparison with standard quantum phase transition. To compare them, let's look at left, and we observe that we have a cross of levels between the fundamental ground state. And the first excited state, we have a cross of levels, and therefore for this value of the parameter, we have a quantum phase transition. And in the other side, we have an example of SQPT, which is basically this same phenomena of high density of levels or even crossing of levels, but in the excited state part of the spectrum. So now that we have clear that what these excited state quantum phase transitions are, at this point they had been basically found in O2O models with collective symmetries, and because they could be corresponded, the parameter exactly in which you have an SQPT could be corresponded with stationary points in the semi-classical Hamiltonian. The thing is that in more general system in which we don't have semi-classical limit and we don't have these really collective symmetries, how can we find them? And can they even show up? This was an open problem. And what we notice is that for Berry-SM theorem, as the variance in the thermodynamic limit goes to 0, a Gaussian with 0 variance, the limit of 0 variance of the Gaussian is basically a delta Dirac function. We can qualitatively observe this behavior in our simulation, as when we increase system size, we observe that the density of a state gets sharper and sharper, approaching a delta function. So basically, the only singularity that we can have is the one of regarding accumulation of levels around the mean value of the density of states, but we cannot have rich phenomena or singularities which imply interesting phenomena. So we conclude that SQPTs are heavily constrained in general models, both long range and local, unless you have a special symmetry which make the variance to not scale, and therefore Berry-SM theorem do not hold. And we observe the same picture for alpha for the strong long range regime in the numerics. So we conclude that these SQPT phenomena are really weird phenomena that only happen in really special models, probably. So now let's talk about the conclusion of our works. Okay, when looking back to the alpha line, we were able to study alpha line in the regime from dimensionality to up to local models, and in all this regime we noticed that partition function behaves similarly, which is and therefore we have common statistical properties, absence of criticality, but the main difference with respect to local models is that for estimating partition functions classically, in long range we have a sub-exponential algorithm, but in local models we have a polynomial algorithm system, and therefore an efficient one. So this is the main difference that we find in this regime with respect to completely local models. And also we remember that there was a quantum algorithm that could perform more efficiently this same task of estimating partition function of long range models. So this opens the question that, okay, maybe there is quantum advantage for estimating partition function of long range models. But well, what we think is that likely there is simply more work needed to do on classical algorithms. But there is work that is needed to do. And also, we think that because this tool that we will develop, which is the cluster expansion for long-range models, has been really useful to get a lot of important results for local models. We hope that, well, our work will makes possible to extend to long-range systems other important features already known for high-temperature Gibbs state of finite range Hamiltonian, such as efficient Hamiltonian learning, the sudden depth entanglement, and a lot more. So at this point, I want to thank everyone for coming and attending this meeting and for your attention in general. And also, if there is any question, I will be happy to answer it. And well, thank you very much.
Okay, thank you very much, Jorge. And now is the time for questions. So if you have any, go ahead, just open up your mic and go ahead. Okay, I do have a question.
Okay.
Just to it's more of a clarification thing, but when you were
Hmm.
explaining the lemma 1 and theorem 1, can you
Okay.
go back to that slide?
Yeah, totally. Okay. This one?
Yes. Okay. So
Okay.
what I understand is that from lemma 1, you take this condition and you transform it into your theorem 1 and prove that they are that you can prove the convergence in a similar way, no?
Yes, exactly. Basically, this lemma, what it gives us a condition. Yeah, yes, it gives us a condition for convergence of the cluster expansion. So our theorem, well, this is a non-formal way to state it, but yes, basically,
Okay,
so basically, yeah.
how does the complexity compare with, I mean, testing your theorem has some complexity. That's the complexity of your algorithm that you showed in the table, no, of comparison. So
Yeah.
how does it compare with trying to test lemma 1 directly? Like, what's the advantage in?
Okay. I guess the thing is that yes, I guess that it would be more in order to check whether the cluster expansion will converge. I guess it may be more efficient to try to see if the Koteckỳ-Preiss criteria is satisfied. But the thing is that our algorithm, what it does is to compute the cluster expansion.
Okay.
So, so yes, if depending on what you want, it may be more convenient to do that. That's like it would be a more intelligent idea. I agree with you. But in order to to do the concrete thing that we are doing, I don't think that you could do it like that. Maybe I have to think about it, but I don't think so.
Okay. So your theorem, like the contribution is more of so the complexity that you showed is the complexity of the actual computation of the partition function, no?
Well, the thing is that, yeah, not, well, yes, but not only because, well, the thing is that this criteria here, okay, it's like a general statement, but it is not applied to any kind of system. So the thing is that this criteria was already proven to be satisfied for local models, but what we didn't know is that it could be satisfied for long range models.
Okay. Thank
Yes.
you.
No, thank you for your question.
Hello, Jorge. I have a question about about your definition of polymers. Can you go to that slide, please?
Yeah. Yes.
Oh, yeah, right. So, yeah, my first question is about these separations. So, as far as I understood, these polymers are basically sets of hyperedges with some overlapping vertex. But if you take, for example, any common Hamiltonian, I don't know, take Ising, in the end, and I guess these hyperedges, you take them from the different terms of the Hamiltonian, all of them are overlapping. So it's just some decomposition in that way, or I'm not really clear on this.
No, yes. That's a good question. Yes, the thing I maybe I was not so clear on this. Like the thing is that for example, in the Ising model, you will have hyperedges. Well, for example, let's imagine it here. You will have this edge, you will have this edge, you will have this edge, you will have this one. Oh, okay. Do you see my mouse? Because
yeah, I see it.
Okay, okay. If not, I'm doing. Okay, yeah. The thing is, when you expand the partition function, you will have a term which will be the Hamiltonian multiplied by the Hamiltonian.
Okay.
And therefore, you will get terms which is the multiplication, for example, of this edge with this other edge.
Oh, okay.
When you expand like the partition function, you will get like a lot of terms. So yes, basically, like these terms of the expansion are not strictly the edges of the Hamiltonian, but all the combination of all the possible edges of the Hamiltonian.
Ah, okay, I see.
So you
Okay.
can combine edges that are disconnected, even though the model you have a complete connectivity in some sense. So yeah, but yes,
Okay.
that was yeah. Maybe
Great,
I could.
thanks.
Thanks for your question.
Okay, so thank you everyone for attending, and thank you Jorge for the really nice talk. I hope to see you all in the next seminars starting September. Bye everyone. Thank you.
Bye.